bounding box, a confidence score, and it classifies every one of these bounding boxes independently. Now the first change that we made to YOLO is that we removed the classification output. So we basically used class-specific anchors. So the first output was always the ball, the second ball was always the crossing, the third one the robot, and the fourth one the goalpost. And we could do that because usually we could more or less guarantee that there's, in a single grid cell, there's only one object at a time of a given class. So there will be no balls or no two balls in a single grid. The only mild exception is the robot, which robots might be cluttered, but if they were, we just drew a single bounding box for two or more robots. And the other thing is that YOLO predicts the width and the height of the bounding box relative to a so-called anchor box, which is a reference bounding box, which in the traditional YOLO is computed using clustering. But since we had class-specific anchors, class-specific outputs, we didn't need to do any clustering, we just used the mean of the bounding boxes that are in the class. So what this did is that we removed the classification outputs, less outputs in the end of the network, that means less rates, big less chance of it. The other thing we did is that we changed the underlying network architecture. We still use the fully convolutional neural network, just a much smaller one than the one that is called a Tiny YOLO. And we call this the ROBO architecture, which I was too lazy to invent a full name of it that abbreviates to YOLO, to ROBO, just called it that. So this one runs about 160 million operations on a close to VGA image. The reason we use this seemingly weird resolution is that if you look at the actual architecture, which is on the left side, the ROBO architecture, it has 6 strided convolutional layers that are down scaling layers. So it has a total stride of 64, and in that case it made sense for both of the sides of the image to be multiples of 64. Now, I already mentioned that we don't use pooling, because max pooling throws away spatial information. Strided convolution could, in theory, preserve some of the important local position information when downscaling. Also, we detect classes at multiple scales, but no upscaling. So instead of adding an upscaling at the end of the network and then having the upscaled output from there, we simply add the upscaled output before the last strided convolution. And of course, the higher scale detection helps us to detect small objects like the balls and the line crossing more accurately. So the first two classes, balls and line crosses, are detected at a higher scale, and robots and goalposts are detected at the finer output. We also have multiple versions of this network. The one you see on the right is the bottleneck version, which is more or less identical, except the channel counts are double, and we have a few bottleneck layers to save computation. We also have a half resolution version, which gets an input image that is half that displayed resolution, and it's missing the first downscaling layer, so it's the same as the left one, except the first layer is missing, so the input image goes in the second layer directly. Right, we pre-trained the network on a synthetic data set that was created using the generator created by Tim Hess, who's probably here. Yeah, shout out to Tim. We created about 5,000 training images, and of course the labels were generated automatically. This is used for pre-training. And we had a small real data set for fine-tuning, which was hand-labeled. It included 4 locations and 700 images, and I spent most of my time here hand-labeling the other 1,400 that are going to be released soon. And as soon is real soon, because they're already labeled, so I just need to double-check them and upload them. So these are used for fine-tuning. And we did a little trick during the fine-tuning step that we called synthetic transfer learning. If you're familiar with transfer learning, it's the idea that you pre-train the neural network on task A that has a large data set, and then you use the features learned to fine-tune it to a different task, and you only need to retrain the last couple of layers because they're the task-specific ones. So when you're switching from task A to task B, only the last few layers have to be retrained, the rest can be fine-tuned or just left as is. Now, in this case, our problem is slightly different because we have the same task, just different input sources. So instead of retraining the last task-specific layers, we are retraining the first couple of input-specific layers of the network, and then we fine-tune the rest using the dataset, like with a smaller learning rate. And one good thing with this is that usually on most neural networks, as you, the first few layers have much fewer parameters than the last couple of layers. Another thing that we did during training is that we pruned the network, which means setting the insignificant weights to 0 so that you could skip the computation and therefore speed up the network. And instead of pruning after the fine-tuning step, we were using L1 regularization, which naturally results in a sparse weight matrix. So during training, by setting the regularization weights, we could get several different models with a certain ratio of the weights pruned. As you can see, we got up to like 93 to 97% of the weight, all the weights zeroed out, and it resulted in a minimal drop in the mean average precision of the network on the test set. Even the fine-tuned, the half-res version only went down to about slightly above 80 MAP, whereas it resulted in a significant drop in the amount of operations required. So we went down from around 150, 160 million operations required down to like 35 to 50. Which of course the amount of weights pruned is not, so there's not a one-to-one relationship with the amount of time you save on the computation, because if you prune a weight from the first layers where the spatial resolution is large, then you save a lot more computation time than in the last layers. But the last layers are the ones that have the most weights, so those are the ones that get pruned. Right, so our results show we compared the network with the Tiny YOLO version 3, and we used mean average precision on the test set to evaluate them. Instead of using intersection over union to evaluate whether the bounding box is good, we used the pixel, so the distance between the centers of the bounding boxes, because intersection over union unfairly punishes tiny object, because a very tiny localization error gives you a really bad IOU if your objects are tiny, and in this case we had 2 classes out of 4 which are usually tiny, and the goalpost is also usually tiny in one direction. We also use the IOU, but I'm showing you these numbers because they look better, although the conclusions also hold if you use the IOU. So what you can see is that on a Tiny YOLO is slightly better than our models on relatively strict localization requirement, but as we loosen like a medium level of strictness or a really loose localization requirement, then our models start to outperform Tiny YOLO quite a bit, and which leads us to conclude that our models are better at telling whether there's an object in a certain position or not. They're just not as good as at localizing it accurately, right? Which is arguably the less important of the two things. Right, we also evaluated the runtime on the Null V6 using a single camera image and a single core. And we used the pruned versions, and you can see that the half resolution, it runs at 13 FPS. The full resolution is around 7 FPS. We didn't measure the Tiny YOLO runtime because it's probably more than 10 seconds. But we didn't bother to run it because it's got at least 150 times more computation, so it's obviously going to be slower. Right, so to conclude it all, we propose a new network architecture that has about, depending on which version you compare it, the unpruned ROBO architecture is about 30 times less computations than the Tiny YOLO V3. The pruned half-res version is about 170 times less computations, and we achieved significantly better mean average precision on medium and loose accuracy criteria. And of course, all our code, the dataset, and the pre-trained models are uploaded to GitHub, so you can use them if you wish. Now, as for further research, we are heavily thinking about using group L1 regularization, because that, instead of pruning individual weights, it prunes entire convolutional filters, which makes more sense in convolutional neural networks, and it will also result in a speed up on GPUs. So that was all I wanted to say, and thank you for your attention.
Thank you very much. Do we have questions?
Hello. When you're doing synthetic learning, how do you choose which of the first layers are you going to retrain? Is it just the first, or always 2 or 3 layers, or how do you make that choice?
So we tried different options and compare them, and whichever worked best, we chose that one.
Okay, thank you.
More questions? There should be more questions. There's lots of teams who do YOLO. Okay, so we're doing YOLO too. Now, you said one of the biggest problems is the labeling in the beginning. Do you have any ideas of how to automatically label?
Well, you could also always use a different algorithm to do automatic labeling, but that kind of is sort of a chicken and egg problem. Like how do you so if you use an algorithm a better algorithm to create good labels, then why do you need to label images for? What do you need the images for if you can already label them automatically? It's kind of.
And did you do any work on how many images you need per object that you learn?
No, I did not check that. But the generalization is relatively good, even with the small data set, and it was improved. We already trained on the larger data set, but I didn't show that results because they were not the ones published in the paper, but they are similar. The results.
More questions in the meantime? Maybe one more question for transfer learning. So how many of those, did you use any of those pre-trained objects from your lab when you came here? Or did you just throw everything away and start from scratch here?
You mean did you use the pre?
Did you come with a pre-trained network from your lab?
Yeah. Yes, of course.
All right. So thank our speaker one more time. So, Hafiz, may I ask you to come forward? So our next speaker is talking about utilizing temporal information in deep convolutional networks for efficient soccer ball detection and tracking. The paper has 4 authors and it's presented by Hafiz Farah.
Hello everybody.
There's no lunch break yet.
Okay, thank you. My name is Hafiz. I'm a PhD student at the University of Bonn, Autonomous Intelligent Group. I'm working in Team Nimro. This work is mostly done by Anna and Mohammed, which are 2 of my students, but they couldn't come, so I will present it. So in contrast to existing method where only the current frame or the image is used for detection, we wanted to have something which can work on a history of multiple frames. Using history allows us to efficiently track the ball in the situation where the ball is disappeared or get partially occluded, and exploiting spatial temporal correlation for ball detection based on the trajectory of the movement of the ball is needed. And of course, we are in RoboCup, so we need something to work in real time. We experimented with temporal convolutional network, TCN, convalescentium, and ConGRU. So we first solved the detection task on one image using fully convolutional encoder-decoder architecture, and later we use it as an input to the temporal model and jointly learn them for the detection of the ball. We present our empirical result to support the effectiveness of our method using the history of ball on challenging scenarios. So this is the overall picture of the architecture. In the right, you can see it. We have encoder-decoder architecture. It has, in the feed-forward part, we have 18 convolutional layers. It is based on SlightlyNet version 1. We added temporal layers after the feed-forward model, and we added a learnable weight W. So we first started with single frame detection, and we formulated it as a binary pixel-wise classification problem. The feed-forward model predicts the heat map corresponding to the soccer ball. Yes. So we tested SlightlyNet 1, SlightlyNet 2, and SlightlyNet 3. All three networks are based on encoder-decoder design. They have some modification to have less parameters. SlightlyNet 1 consists of 5 blocks in the encoder part and 2 blocks in the decoder part. The number of filters is doubled after every block. In the decoder part, both blocks contain 3 layers. Each layer contains a convolutional operation followed by batch norm and value. Bilinear upsampling is used twice after each block of encoder and after the first block of the decoder. Skip connections are used to preserve the fine-grained detail from encoder to decoder. This is commonly used in many segmentation networks like UNet, VNet. All convolutional filters across the layers are the fixed size of 3 by 3. The encoder part includes 4 max pooling layers, where each one is put after the first 4 blocks. So then we added the temporal part, which used multi-frame detection. Temporal part, we experimented with 3 different models, as I mentioned. We take into the account of each previous frames, namely in this experiment 20, and then we predict P frames afterward, which is in our case 1 frame. So we get 20 frames and we wanted to predict 1 frame in the future. Convolutional structure avoids the use of redundant non-local spatial data and result in lower computation, of course. We also take advantage of high resolution spatial information by concatenating the output of the second and sixth blocks, and we had a learnable W to combine these information. To speed up the training process and propagate spatial information, we apply the convolution of size 7 by 7 on the combined features. We also take the element-wise product output of the convolution with a learnable weight W. So the TCN, which is recently proposed, is encoder-decoder, which is, in our experiment, we used 64 and 96 channels, and instead of using the SGD, which was proposed in the original paper, we used Adam and we used NSULOS in our experiment. We also used LSTM and CompGRU with 4 layers of 32, 64, and 32 and 1 different channels. The critical advantage of TCN is that it will give you the real-time performance that you would need on your real hardware, and it uses a dilated causal convolutional layers. Overall, the performance is comparable with CompLSTM and CompGRU, but it is faster. In the left, you can see the architecture of TCN, and in the right, you can see CompLSTM, which is completely standard. So we did use a synthetic dataset to pre-train our temporal model, and here you can see experiment which is done on the synthetic data, and we excluded the ball in some frames to resemble the occlusion, and as you can see, the ball is not detected in some of them, but after frame 20, the next prediction is having the ball, so the method can work even when the history has some partial or fully occluded balls. We also tested on more challenging scenarios, like when we have multiple detections or multiple balls in the scene, and the method can well generalize to multiple ball tracking and detection, although it was trained only on one ball. In the left, you can see the output of feedforward network or threading-net network. In the B image, you can see the residual information, and in the C, you can see the ground truth, and D is what we produced after the temporal part. As you can see, the output of threading-net, one of the ball is not has high response, so it might cause a false detection, a false negative detection. And after doing our temporal corrections, we can have it fully. So we created a data set of around 4,500 images, and around 4,000 of them has images of all. Since the data recorded on walking robots, many of the data has blurry data, and we used a standard way of evaluating detections using FDR, PR, and RC. Each image is represented by a bounding box with coordinate x min, x, y max, x max, and y max. Sorry, I cannot read that without glasses. That good. For teaching signal, we generated a binormal probability distribution centered over the center of the bounding box, and in contrast to threading-net, we also detect and produce the radius of the ball. So here you can see 3 different images in the history. In the left you can see the residual information, and you can see our ground truth and the output of our network. Here, for example, threading-net doesn't produce a high response, but after doing the temporal model, we can produce a high response. So, in general, when we misdetect some ball or when it is occluded for some frames, we can persist recording the ball to the higher levels. So, here are more examples. As you can see, our robot fitted with a wide-angle lens, which poses more difficulty than just a normal camera. Here you can see the pseudocode of the way that we produce the synthetic data, and in the left how we calculate the centroid point. For post-processing, since the output is has a spatially lower resolution than the original image, which is VGA, we have to do some post-processing. We first find the contour of the response, and then we report the mass centroid of the contour, and this will give us the ability to report with sub-pixel accuracy. For inference, we used our Mimbro OP2X robot. It has Intel Core i7, it has 8 GB of memory, and it has a 4 GB GTX 1050 Ti NVIDIA GeForce GPU. This is the result of comparison different models of SweatyNet, and we concluded that SweatyNet with a probability of 0.5 for dropout would be best suited for our data set, so we used that as the feed-forward model. In the left, you can see the report of inference on the robot. SweatyNet takes around 4 or 5 milliseconds for inference, and LSTM and GRU are not that well suited for our application, but TCN would definitely be a suitable choice. And in the right, you can see the detailed report of our experiment. Real means that we only trained it on real data for the temporal part, and FT means that we first pre-trained it with synthetic data set, and then we fine-tuned it with the real data. So we observed that when temporal model is pre-trained on artificial data, the learnable weight W gets the weight of 0.57, which means that it uses the data from the previous layers and it does something meaningful for us. With transfer learning, we could leverage the knowledge of learned information from synthetic data set. So in conclusion, using temporal information can help fault detection and tracking. The sequential network successfully captured temporal dependencies and give an improvement over SweatyNet. Usage of artificial data for pre-training the temporal network is beneficial due to the shortage of real data sets, and TCN is the best choice for our application. We released our source code and dataset on GitHub. Thank you.
Thank you very much.